All right, so this next section, we're still talking about integration, right? Integration, when anyone says integration in mathematics, it means finding the area of this aqua color here, right? You've been finding area for a while, but they're regular shapes, right? Rectangles, trapezoids, squares, right? It's easy when it's shapes, but when it's kind of like this, kind of a blob thing, it's very hard to find the exact area. It's not hard, but it's more difficult, right? That's what we use integration for. That's the purpose of integration. Finding area for things that are not nice and pretty shapes. Okay? So there's three ways to do that. Three ways to do that. Number one, we've done already. We did already. We did a little bit last week and then we finished it yesterday, right? Approximating it using triangles and trapezoids, right? Triangles and trapezoids. That's the last set of notes that we did. We started it last week and then we finished the trapezoid part yesterday. Okay, that's one way. Problem is, it works. The problem is, it's an approximation. It's not exact. Okay, so it's a good approximation, but it's not exact. The 2 and 3 are the ways to do it exactly. Okay, so we're going to do today. Um, we're going to do number 2. Okay, we're going to use geometry. Geometry is just the study of shapes. Okay, so the shapes that we see today are shapes we've seen before, right? This is not a real shape. This is not a, so we'll put off those for next week. Okay, that's number 3. We're going to spend really the rest of the semester finding area of kind of these kind of things. So this number 3 we'll do next week, and pretty much like I said, until not the rest of the semester, but the rest of this unit. Okay, so today we're going to focus on number 2. Before I go on though, so the third method is the what method we're going to use most often. This is the method you're going to use almost always. And it takes a little bit of time. Okay, so we won't do a chapter test until we finish number 3. That's going to take a few weeks, right? So before we start number 3, I want to give you guys. So we're going to have a quiz. Okay, so we're going to have a quiz that'll cover these two right here. Okay, and antiderivatives. Okay, so probably let's see. So again, let's see today. It'll probably be early next week quiz. So it's not anything that's going to happen tomorrow or the day after, but it's just something in the back of your head. Okay, so I should start. We're going to have a quiz. We're going to start, start preparing yourself for a quiz. Okay, so that'll cover 3 things. The first thing we did for this is antiderivatives. How to find the antiderivatives, to use the power rule, right? We did that. This is the last lesson that we just covered. That'll be on there. And then this lesson here that we're going to do for the next few days. Okay, that's all. It'll cover those 3 things. It's going to be a very short quiz, maybe 5 questions tops. Okay, so just somewhere, I'll post it, the exact date on Google Classroom, so you'll know exactly when it's coming. But I just want to kind of give you a heads up as to our first quiz. Okay, and then after we finish this guy here, then we'll take the chapter test. Okay, but again, this guy here is going to take a few weeks. Okay, so I just want to get a quiz in there before we start doing number 3. Okay, so these are the 3 ways to find area under the curve. Okay, so today again, we're going to focus on number 2 today. All right. Okay, so I told you guys last week, I think, when we started doing this, maybe the week before, why this dx part, right? I was like, so like, for example, if we're trying to find the area under this curve here, we would write it as the area from A to B, right? Those are the bounds. It goes from A to B for this function here, f of x. And then we always put this dx, right? And I was like, don't worry about the dx. When we did antiderivatives, don't worry about it. I'll tell you about it later. Just include it. Today, I'm going to explain why we need it, why it's a big part of integration. Okay? Okay, so, all right. So, a lot of notations here. If we make sure subintervals are all the same width, we can increase the number of rectangles to use an infinite to infinity using a limit of the Riemann sums. Okay, so this guy right here looks very, very complicated, but it's not. You know each part, right? So when we did rectangles, right? When we were doing rectangles, we found that some of the rectangles were an overestimation and some of them were an underestimation, right? Let me give you an example right here, right? Some of them were overestimation and some of them were an underestimation. Well, to find the true area without being over or under, right? LRAM, this case, LRAM was under, RRAM was over. So in order for me to use rectangles to find the exact area, what I would do is slice the rectangles into smaller pieces, right? So if I slice them into smaller pieces, so instead of being half width, right? Width of half a unit, make them into smaller. Because if I make rectangles into smaller rectangles, they'll close up some of these dead areas here, right, that aren't being covered. And if I make them smaller rectangles, so if I make this guy has to go up here because it's RRAM, right? But if I made a rectangle like that width, then it doesn't have to, right? If I make a rectangle that width, it doesn't have to go over, right? So the idea of integration comes from rectangles, but we want to set up a system where we don't overestimate or underestimate. So in order to do that, we need an infinite number of rectangles. If I had an infinite number of rectangles, just like this, set up just like this, they would be so thin that none of them would go over the blue line or be too low. So it would cover it perfectly, right? That's the idea of integration. So this part here is the number of rectangles as the number approaches infinity. Okay, that's what this part means, right? To find the perfect area, to find the area and not overestimate or underestimate, I have to have an infinite number of rectangles. That's what this part means here. You guys know what limit means. Limit means we're getting close to something, but we're not actually getting there, right? So as I'm getting close to infinity, as I'm including slicing them up into smaller rectangles, into thinner rectangles, I should say, right? I start with one rectangle and I go until I finish, right? That's what that means. Does anyone know what that E symbol means? It kind of looks like a fancy E. Does anyone know what that means? Has anyone seen this letter before somewhere, anywhere? This letter here? It's a Greek symbol. Exactly. It's summation. It's a summation notation. It means sum. Anytime you see that letter in math, it means you're going to be adding something up. It means you're going to be adding something up. It's a summation notation, they call it. It's the Greek letter sigma. It's capital. Anytime you see this in math, it means I'm going to be taking a total. I'm going to be adding something up. It's a summation notation. Okay, so what am I going to be adding up? Well, what do you think I'm going to be adding up? The areas of each of the rectangles. That's what I'm adding up. The areas of each of the rectangles that will equal the area under the curve. Okay, so that's where that comes from. This part here. Let me use a different color. This part here that looks like a bad word. It's not a bad word, but it looks like it. That represents the height of each rectangle, right? That represents the height of each rectangle. Okay, the height of each rectangle. Now, why does it represent the height? Okay, so let's go back to the questions that we did last time. I'll show them in a second. I just want to let you guys copy that down. I'll come back to this slide in a second, but I just want to show you. How did I determine the height? What was my process for determining how tall this rectangle was here? Do you guys remember? What was my process? There you go, right? Plug it in back into the original. Well, that's what it's saying here. F of CK. CK is the X value. Plug the X value into F. That's why the F is there. And that'll give you the height, right? That's what we did. Okay, so that'll determine the height. Well, there's one thing we're missing. I have the height of each rectangle. I need to multiply that times the width, right? Or the base. That's what the delta X. That's what this guy represents. The width of each rectangle. The width of each rectangle. Okay. Delta, the triangle looking thing, triangle looking character, is another Greek symbol. Probably heard of it before. The Delta variant, right? It was before Omicron, and for COVID-19, where, you know, the big one is Omicron right now. The one before that was Delta, right? That's what they're talking about, Greek letters, Delta. In math or in science, what does delta mean? Does anyone know what delta stands for or means? Exactly, change. A change in something. A change in something. How fast something changes. Like sometimes we talk about slope in math. We talk about slope. Sometimes you'll see that symbol, change. Like you'll see the slope. Slope of a line equals the change in y over the change in x. Right? That's how I learned it back when I was, you know, taking algebra. They don't use those symbols anymore, but that's what it means. It's just change. It's just change. Anytime it changes. Well, that's what. How much is x changing? Okay. So if x is changing, that's the width, right? That's the width, right? How much x? Because x determines the width. Y determines the height. Oops. Right. X determines the width. Y determines the height. Right. So that's all of those parts have meaning to them. Now, luckily, you don't have to see this. You won't see this probably after today. You won't see this form because it's been replaced with this form here that we've used before, right? But believe it or not, this came from the limit, okay? So I'll break it down where it is. Okay, so the summation notation of sigma has been replaced by this guy here. So this guy here is this guy here. Okay. So when we see that integration symbol, that antiderivative symbol, right? That's telling me I need to go from A to B. So how many rectangles am I going to need? Right? That's the function of that symbol. Okay. The f of x, that's the function, right? I plug in x to get the height. So that's going to tell me the height. F of x is going to tell me the height. Okay. Well, what about the width? What's going to tell you the width? This guy right here. That's why the dx is important, because it tells us the width of each rectangle. And without a width, you can't find the area of a rectangle. Okay, so that's why it's important. So all of that is done to show why we need each part. Why do I need the integration? Because it tells me how many rectangles I'm going to have, from where to where. Where do I start to where do I end? Why is f of x? Why is the function important? Well, that's going to tell me the height. Why is that dx that I've been writing down for a few weeks that Mr. Flores said don't worry about right now? Why is it important? Because that dx represents the width of each of those rectangles. Okay? That's why it's important. Okay? That's why each of those pieces is important. Okay? So like I said, the top up here, this part right here, besides today, or if you're looking at a textbook, you probably won't ever see this. Okay, because it's been simplified down to this guy here, which you will see many, many times, right? But they all mean the same thing, right? This tells me my bounds and where, how many rectangles I'm going to need, right? This tells me my height of the rectangles, and this tells me the width of the rectangles. Now, when we use this formula here, we're basing it off using an infinite number of rectangles. Okay, I can't draw that. I can't draw an infinite number of rectangles. So that's why when we use this guy here, we're not going to draw the picture, right? We're going to use other methods, one of which is we're going to do today. Okay, so when you're reading this guy, this is how you read it. The integral, that's the S part, of f of x from a to b. So if you're reading this question here, you would say the integral of f of x from a to b. Or if you actually put a function here, let's make one up. Let's say that one. We would say the integral of 5x plus 1 from 2 to 4. Integral tells me area under the curve. The function tells me height. And this will tell me how many, and 2 to 4 tells me what's the width, how far is the area, how far from beginning to end. We don't really say the dx part, we kind of just assume that part when we say it out loud, but we always write it. So it's always important. So why is it always there? Why is that part there? Hint, hint, you might see this on a quiz. Why is that dx part there? Because it represents the width of the rectangles used to find the area. Okay? Why is that dx there? Because you're going to see it a lot. And it might make you angry because it doesn't serve any purpose, and you might lose a point because you don't have it there on a free response question. And you're like, well, why do I need? That's why. So I might put that on a quiz. Why is that dx part? What is the function of that dx part? Okay. Okay. That's the background I was promising you guys. Okay, that was the background. I did all of that pretty much to explain why this guy needs to be there. Okay. Okay, so let's look at a question. All right, so now we're going to be finding the exact area. No more approximation rectangles. We're not going to be doing that anymore. So today what we're going to do is so we can define the area under the curve of a function from a to b as an integral from a to b. We just talked about that. So for these two, I'm going to use geometry. Geometry means make a shape. Make a shape that I know how to find area of, right? This guy here probably couldn't do that for this guy here, right? Because that's not a shape I recognize. But the ones you see today, you will be able to, okay? So the first thing we're going to do is draw a picture. The first thing you're going to do is draw a picture because I can't see a shape unless I draw it, okay? So the function. So for letter A, 1A, what is the function we need to graph there? Can anyone tell me what the function we need to graph for? What's the function there? Yep. Just 3. Yeah, just 3. That's the function, right? There's no x, there's no variable, it's just 3. It's a constant, right? So let's draw that from 2 to 9. Okay, so I'm going to draw a quick sketch here. I'm going to go from 2 to 9. 4, 5, 6, 7, 8, 9. Okay. So I know it starts at 2 and ends at 9. Those are the bounds. How do I draw the function? Because this is f of x, right? This is f of x. How do I draw 3? How do I graph that, I should say? How do I graph 3? Is it a line? Is it a curve? Yeah, Rum? There you go. That's all it is. Everywhere, it's always y equals 3. It's really y equals 3. F of x equals 3. That's what Yuvraj said. It's the same thing, right? 1, 2, 3. 1, 2, 3. Just like Roman said, it's everywhere 3 exists. That's just a straight line. So I'm only going to go from 2 to 9 because that's all I care about. I don't care about anything before or after that. Okay? Area under the curve. Area under the curve to the x-axis. So that's this part right here, right? Well, that shape looks familiar, right? What is that shape? It's a rectangle. Yeah, it's a rectangle. The width, just one big rectangle. It's a 7. The height is 3. 21. So this equals 21. Okay, but you wouldn't see that unless you actually drew it, right? You wouldn't know that it's a rectangle. You might now know it, but before you did that, you might not know what it is. Like the second one, like B. I have no idea what shape that's going to be. I have no idea what shape it's going to be until I draw it. It's not that big, and it's not a very complicated function. Okay? So it only goes from -2 to +1. So that's all I'm going to draw. I don't care what happens before -2 or after +1. I really don't because that's not part of the function. So really, I'm just going to focus in here. Okay, that's the function there. Absolute value. So what does absolute value mean again? Remind me what absolute value means. There you go. How far a number is from 0. So if I'm at -2, how many steps is it back to 0? 2. +2 or -2? +2 or -2? Always positive, right? You can't take negative steps, right? We'll always take positive steps. So that being said, that's how you graph it. So let's start making dots. So I need to know where it is from -2 to 1. So at -2, when I plug in -2 here to x, what do I get? +2. So make a dot there. -2, +2. -1. What dot or what not dot? What value do I get when I plug in -1 into f of x? +1. How about 0? How many steps from 0 is 0? None. It's already on there, right? And then how about 1? What's the absolute value of +1? 1. Done. Close it off. Well, this one looks familiar and this one looks familiar, right? They're two triangles. So I need to find the area of this triangle plus the area of that triangle. Add them together. Okay. So the first triangle, it's got a base of 2. Right? It's got a base of 2, and the height is 2 as well. So 2 times 2 divided by 2, we get 2. So this guy is 2. The area of this guy is positive 2. This guy here, it's got a base of 1, and it's got a height of 1. 1 times 1 divided by 1, or sorry, 1 times 1 divided by 2. 1/2, right? 0.5. Add them together. 2.5. Okay. So we didn't need to approximate. That's actually the area. That's actually the area under that curve. Area under the curve for this guy is 2.5. Okay, it's not an approximation like we were doing last unit. Okay, it's an actual. All right, letter C here. All right, so what I want you to do is I want you to graph letter C. Graph it, we'll do it together. Okay, so graph it from -3 to +3. I'll give you a hint. It's going to be curvy. It won't be rigid lines. It'll be something curvy. That's okay. It'll look familiar when you see it. It's going to have some curve to it. It's not going to be rigid straight lines. It's going to be curvy. So make all your dots and then kind of draw it with a curve. So when you plug in -2, it becomes +4. Right? -2 squared, +4. So 9 minus 4 is 5. So the square root of 5. Square root of 5 is about 2, a little over 2. And then if you plug in 1, 1's negative, or sorry, -1. -1 squared is 1. So the square root of 8 is a little bit less than 3. A little bit less than 3. So you kind of start seeing this shape formed like that. And then, actually more like that. And then you start seeing this shape like this as well. Okay. So it could be half circle, could be a half oval. How do I tell the difference between a half circle or a half oval? How do I know which one that's going to be? Yeah, Rum?
It has to have the same radius all around the circle.
Exactly. Is it always the same radius from the center, right? So this is the center here. Right here, it looks like it's 3 units away, right? Right here, it looks like it's 3 units away. That's a circle, right? If one was 2 units and one was 4 units, then that's an oval. But it's not. It's the same, right? It's the same. That's the definition of a circle. A shape where every point is equal distance from the center. Okay. Okay. So it's a circle. It's a half circle. So we just got to find the area under the curve. Alrighty. So area under the curve is right here. So the area of a circle is pi r squared, right? And if I want half a circle, that's just divided by 2 or take half of it. So that's the area, that's the formula I'm going to use. Okay. So the radius is 3 because from the center to an edge is 3. Either way I go. Oops. So 3 squared times pi over 2. 3 squared is 9, so 9 pi over 2. Most of the time, you'll leave it like that. Okay? Most of the time, like I said, I've never seen them say on a test or a quiz, change that to a decimal. Never seen it. It'll always be in pi. Leave it as pi. The reason being, because I could use my calculator to do that question here. I can use my calculator to do it, but your calculator won't give it to you in terms of pi. It'll give you a decimal. So that's kind of how, that's why they do that way. Okay. Okay, so now we're going to do the same thing, but now we have another conundrum here. So now example number 2. So what happens if the area is not above the x-axis? It's below the x-axis, like this guy. Let's draw the picture here. So I got my bounds go from -8 to +2, from -8 to +2. Okay, so let's draw that. Let's sketch that. The graph's already done for you. So just kind of shade where the area is going to be. So -8 is here, right? So this is the bound here to over here. So when I say area under the curve, make it a little darker so you can see it. So there's one bound. No, I want to use a different color so it doesn't make you think it's part of the function. There's one edge. There's the other edge. So when I say area under the curve, you automatically look below, right? So this guy, it'll be like this, right? So that's part of the area in the green there. What about this part here? Where do you think I'm going to shade here? Because if I shade below, that's all of this, right? So I can't really shade below this line right here, right? So what do? There you go. Always shade towards the x-axis. That's a good way to remind yourself. Always shade back towards the x-axis. So here, I'm not shading below, I'm actually shading above. Let me write that down. That's a good way to think about it. Always shade back toward x-axis. Always shade back toward x-axis. So if you're ever drawing this or ever sketching it or ever shading it, always shade back toward the x-axis. So sometimes that might be below, sometimes it might be above. Okay? That's the first thing. Good. The second thing is, if I do have any area below the x-axis, we consider it a negative value. I know area, so area can't be negative, right? Area has to be positive. But in this case, even though area is inherently positive, a Riemann sum and an integral can have negative values. Okay, so this is really the only time when you're going to have a negative area. So anything above the x-axis, probably should have shaded a different color. Let me shade it a different color. So the dark part is area, but it's a negative area. So whatever I get is going to be a negative answer. And I'm going to add that with the positive part. Okay. Okay. So let's find area of this guy first. Dark part first. So this is a triangle. The dark part here is a triangle with a base of 4. So what I do is I picture it all positive, and then whatever my answer is, I just change it to a negative answer because I know it's under the curve. Okay? The height here is going to be 8. So area of a triangle is base times height divided by 2. So 32 divided by 2 is 16. But since it's under, I just change it to a negative 16. So you find area the same exact way. You just subtract it, or you just make it negative. All you do is change the sign. Okay, so that's going to be a negative 16. So to find area of this guy here, I'm going to have to go negative 16 plus something. Now I need to find the area of the green stuff. This one's a little more tricky. How do I find area of that green stuff? You don't need calculus to be able to find area of that green stuff. You guys have probably done stuff like this back in 7th or 8th grade. I can't remember where you guys do area. Tricky little shapes like this. How am I going to find area of that? You rush? You could split it into 3 different shapes, right? You can split it. So you can split it into triangles, trapezoids. It kind of makes it tricky because of this little curve here, right? Half circle thing. The way I would do it is fill this out here. If I were to fill this part in here, that's a shape I recognize, right? That's a trapezoid, right? Base 1 on top, base 2 on the bottom, height here, right? We've done that before. And then I would take away the part that I don't need. What shape is the part that I don't need? What shape is this part here? It's a half circle, yeah, it's a half circle. Find area of that and then subtract them, okay? There's other ways to do it. It's not the only way to do it. That's just the way I saw, okay? So find area, let's picture it let's picture this guy being a whole shape. Okay, so if this guy's a whole shape, this is base 1, this is base 2, and this is the height. Okay, So base 1 is 1, 2, 3, 4 units. Base 2 is 6 units. The height is 4 units. Okay. So 4 plus 6 divided by 2 times 4. So what is that? 5 times 4? 5 times 4 is 20. So 20 is the whole thing. If this was the entire shape, that area is 20. But it's not the entire shape, right? I have to take out this shape here. And this is a half circle. Okay, so let me find area of that shape. So let's see. It looks like this radius right here is, what is that? 1, 2, 2. So 2 pi r, no, pi r squared divided by 2, which is 4 pi over 2, which is just 2 pi. Okay. So I would go 20 minus 2 pi. That's my area there. And that's what I would put here. Again, that has nothing to do with calculus. That's all kind of geometry, finding areas, right? It doesn't say anything about round your answer. So if it doesn't say anything about round your answer, don't change it to a decimal. Okay? It does say write it in simplest form. That just means reduce your answer if you can. That reducing does not mean change it to a decimal. A lot of times students think that. Where reduce your answer. Oh, change it to a decimal. No, that's actually not reducing. That's actually approximating your answer. Okay? So this guy here, though, I got some work to do. Right? I can combine these two guys. Negative 16 plus 20 is 4 minus 2 pi. That is simplest form. They're not like terms, so I just leave them like that. I don't, again, don't change this unless you have to. If your answer, if it said write your answer into the nearest hundredth, then you change this, then do that. But don't do it unless it asks you to. Okay? Because like I said, 99 times out of 100, they're going to have you leave it as a pi. They won't have you change it back to a decimal. Okay? All right. All right, let's see here. Okay, so last thing we're going to do today, I want you to do example number 3. Do example number 3 on your own. Draw the sketch, find the area. Okay? Give you about 4 or 5 minutes, and then we'll be done for today. So I plugged in 4 for x, 5 for x, 6 for x, 7 for x, 8 for x, and I found that I got negative values. And it's aligned, it's linear, because the slope is a -1, the y-intercept is 3, so on and so forth. Okay? It's a trapezoid, and it's under the x-axis. So that means I shade up, and the area is going to be negative. Okay? So let's see, trapezoid. Let's see, the base 1 is 1. Base 2 is 5. The height is going to be here, and that's 4. All right, that's the width of the bounds. So 1 plus 5 divided by 2, and then times 4. So 6 divided by 2 is 3, times 4 is 12. But because it's under the x-axis, it's going to be negative 12. Okay, so what is the area between the curves? So the area is positive 12, but the integral is negative 12 because of that. Okay, because it's under the x-axis. It's all under the x-axis. There is no positive, so I can't add it with anything. Okay. Okay, so you can see that we're going to continue. We haven't finished. We're going to continue these notes. We're going to do some sine, cosine stuff, and then I'm going to show you how to do it on a calculator. I'm going to show you how to do integration on the on your TI calculator. Okay, so we will do that tomorrow.